This is problem 107 from chapter 3. So in this problem, we've got a beaker filled with water, and that has an initial temperature of about 24.5 degrees, and we're told the mass of the water is 32.5 grams. We've got a hot piece of aluminum that has a mass of 15.7 grams. It also has an initial temperature that we're told is 53.2 degrees Celsius. And that hot aluminum block is going to go into the water, and hopefully, obviously, the water temperature is going to rise, and the temperature of the aluminum block is going to decrease. And over time, we should reach a state of what's called thermal equilibrium, where the temperature of the block and the temperature of the water are the same. So as we get into this problem, it's kind of important to look at the energy associated with the aluminum and the energy associated with the water. And so I'm going to make those separate. I'm going to write the aluminum information on the left side, and I'm going to write the information about the water on the right side, and I'm going to try to use a different color of pen and keep those separate, at least in the beginning, so that you can kind of see, follow those things more clearly. So again, mass of aluminum, 15.7, initial temperature of aluminum, 53.2, mass of water, 32.5, initial temperature of water in blue there at 24.5. And then again, we reach thermal equilibrium. And so not only when we reach thermal equilibrium are their final temperatures the same, we also are making an assumption about the energy transfer here. We're making an assumption about the energy transfer that all of the energy lost by the aluminum is gained by the water. And so we're assuming we have an isolated system and that there's no energy loss to the surroundings. So in terms of our equation, that means the Q, or the energy of the aluminum, is equal to the Q of the water. Now I've got to put a negative sign in front of the Q because, one, the aluminum is losing energy, so that's an exothermic reaction, and the water is gaining energy, so that's endothermic. And so in order to equate those, where the exothermic one technically is negative and the endothermic one is positive, I need to throw an extra negative sign in there so that I can really say that the Q of aluminum is equal to the Q of H2O. And so I know that Q is MC delta T. So I need to use the mass of aluminum, specific heat of aluminum, and the temperature change of the aluminum. And then on the right side, I've got the mass of water, specific heat of water, and the change in temperature of the water. So as I continue to solve those, let me caution you that leaving out that negative sign is probably the easiest mistake to make. And you've probably made that mistake as you've been solving algebra problems where you've just not carried the negative sign down from one line to the next. So I'm putting in here the mass of aluminum, the specific heat of aluminum, which I looked up. I don't know the final temperature, but I know the initial temperature, so I can put that in for delta T. And then I can do the same thing for the water. Again, 32.5 grams of water, a specific heat of 4.184 joules per gram times degrees Celsius, and T final minus the initial temperature of the water. Remember that the T finals are going to be the same because we are at thermal equilibrium. And so the rest of this is just simply working out the math and making sure you distribute everything through the T final minus 53.2 on the left side and distributing everything through the T final minus 24.5 on the right side. Don't lose track of that negative sign. And when you carry this all the way through, you're going to end up with the final temperature of this process. And you end up with a final temperature of 27.2 degrees Celsius.